Hello, and welcome to Stardog Academy Training on Virtual Graphs. I'm Al Baker, Vice President of Enterprise Solutions here at Stardog. To let you know a bit more about me, for the past 20 years, I've helped organizations from the likes of NASA to top 5 pharmaceutical companies get the right data to the right people at the right time. Today, I'm going to introduce you to virtual graphs. In this training session, you will learn what a virtual graph is and how to configure them, how to understand virtual mapping to data sources and the options available, and how virtual graphs interact with other features. Let's get started. This section is about virtual graph overview. Now, what is a virtual graph? This is a new feature available in Stardog that enables extending the graph over existing data sources without moving the data, essentially virtualizing that data for use in the knowledge graph. Now, these virtual graphs look like named graphs in the knowledge graph. They just happen to not be data stored within Stardog, but rather the source systems that currently house them. Each virtual graph is going to have 3 key components: a unique name, data source information or administration capabilities about how to access that data source, and then the actual virtual graph mappings that tell Stardog how to take that source system data and represent it within a graph structure. Now, there's lots of different virtual graph sources that Stardog can extend over. Starting out with the most typical, we look at relational databases, things like Oracle, Postgres, and MySQL, to new ones like the big data ones like Apache Hive, AWS Athena, Google's BigQuery, or Spark SQL. Branching out beyond that, we've got support for NoSQL databases like Mongo, Cassandra, Elasticsearch, and so on. We can virtualize other Sparkle engines, including other Stardog instances. Things like cloud services, CRM, and data analytics are also new and exciting virtual graph sources that Stardog is adding with every release. And then last but not least, we have files and unstructured data or semi-structured data that can also be represented via the virtual graph feature and ingested into the Stardog platform. Now, to be clear on where we're sitting in the architecture, here we have an example of a Stardog knowledge graph that is being sourced from 3 different types of data. We've got structured data, semi-structured data, and unstructured data. And in the context of today's talk, we're going to be speaking specifically about the structured data and semi-structured data, which we can use the virtual graph feature to fully virtualize, persist, or cache, and we'll review each option along the way. This concludes the section on virtual graph overview. This section is about data sources. Now, the virtual graph is going to need the data source connection information to connect to. Now, originally, this was created implicitly by adding a virtual graph, and in recent versions of Stardog, we can explicitly manage the data sources as independent configuration options within the platform. This provides a benefit in that we can manage our database connection properties from a single location. Now, any data source Stardog cannot connect to on startup is going to be marked offline and can be administratively brought online later on. There are a whole bunch of data source command line options as well as Stardog Studio administration, both of which we'll be looking at during the course of this presentation. Now within Studio, we can see in the left-hand side of the menu here, we have an icon that when clicked upon gives us our data menu. And then for each one of these data sources, we can see if there's a virtual graph connection, and then some information about that data source. Things like the data source type, the JDBC information, including connection URL, username and password, driver class. These would all be typical connection properties that anyone familiar with database development will have within their ecosystem. Clicking on the Add Data Source button, we essentially get the same information, but in a form. Of note here, there are several available options for providing advanced configuration, setting up connection pools, setting driver options, and other options that may be specific to that data source. So Stardog does not want to provide any specific limitations around those third-party drivers and the types of configuration that you might need to apply to them to successfully use them in a networked environment. This concludes the section on data sources. This section is about mappings. Now, virtual graphs map structured data declaratively into RDF. Essentially, we're going to describe how we take that source information, which could be tables with columns, and turn those into things that look like nodes and edges. And this will be generic as it gets applied across a wide variety of different data source types. Now, the mappings are conceptual, and we can use those in a couple of different ways. We can use them for extract, transform, load, or ETL into RDF. Or more typically, we can use them to query on the fly, which will take those incoming Sparkle queries into the Stardog platform, understand which parts are backed by a virtual graph, and then rewrite that query on the fly to the source language behind, like SQL. Now, to get started, we're going to want to create and edit these mappings, typically within Stardog Studio, where we have a nice user interface to create a new virtual graph. We can select our data source, we have the option to generate mappings, and we can edit mappings using a variety of syntaxes, which we'll look at today. Now, the first syntax that Stardog supports is the W3C standard for R2 RML. And this gives us a couple different types of mappings. First is direct mapping that will be auto-generated off a relational schema, and then a customizable mapping that provides us a vocabulary for structure that we, the author, choose, giving us the flexibility to define the shape of that graph however we see fit. Now, for the purpose of today's training, we're going to look at our music data set in a relational schema. And this one, we're going to follow a certain set of tables following primary and foreign key relationships, as noted here. So we can see a foreign key. For example, in the artist table, we've got a primary key of ID. We see a songwriter table that has the foreign key of writer and a foreign key of song over to the track table. And we want to be able to represent this information within the knowledge graph, elevating these tables and keys and columns to nodes and edges and certain relationships that let you take advantage of this information using graph features. So let's step through and take a look at how we take each one of these tables and start to create a mapping, understanding what is the shape of the graph that we want to make based on these tables. So starting on the right, we look at the artist table, and we see here that we have an ID, a name, and a type column. And the type of graph that we want to make, we're going to take this ID field, and we're going to use it to form something known as a subject URI, templating in that ID value to make a primary identifier within the graph. We also have a fixed type to an artist class here, and then we've taken the name column and made that a literal. Moving on to the album table, we're going to essentially do the same thing with a couple of key differences. First, the ID field here is going to create an album subject URI, again using the M template feature to create a URI using the ID. But then because we know that artist here is a foreign key, we can take the value there and make the artist identifier in that object position. So for the triple album artist, we're using the ID and the foreign key artist here to generate that triple. And so you could view this as just a natural join across the tables where we're using the identifiers as the means to express that within the graph. Moving on to the left, we have the track table. We are going to do the same thing. Here we have a song. It's going to be templated out and pick an identifier for the graph. We have our fixed types and classifications that were added, and a couple of columns that will be represented as literals. And then we also have a foreign key over to album. And you'll notice that we have a directional change here. So this has an album track with the arrow pointing towards song. And so even though we're in the track table, we can create a triple where our foreign key is in the first position, subject, and go album, track, song. And finally, something like a many-to-many table, where here we have songwriter with a song and writer as both foreign keys, we can now make an additional edge using these keys within this table to essentially give us a direct link. And so you'll notice here that we don't really have a many-to-many equivalent table within the graph, but rather we have the logical relationship with the direct arrows linking those two concepts together. And so the many-to-many table is one of the first things that most people will notice kind of fades away as a relational specific artifact that just doesn't match the logical environment that we're going to think about when we start to talk how these nodes relate to each other. Now the R2RML mapping, we can take this and have a couple of key maps within that single mapping file. First will be the triples map, which takes the mapping from one row of a relational table to the RDF triple, a subject map that talks about how that subject is formed, and then each one of the predicate object maps showing how those columns map to certain predicates. So this is what that looks like using Stardog Studio. There's a separate icon and menu item here for the virtual graphs, and this will populate the editor window with whatever the virtual graph mapping is. In this case, the example shown is an R2RML mapping. Now, as in all RDF, we can read this as a sentence. So we have a mapping is a triples map, and we've got our logical table where we express our SQL query. We then have our subject map, which has the template form to creating those subject URIs, as well as the class to associate with each subject that we create. And that gave us that fixed is a class type that we saw in the diagram. There are then a series of predicate object maps, essentially for each of the columns that we saw in the relational side. And then in cases where we know that the column represents a foreign key, we have a templated URI as well. Now, R2RML is just one syntax. We have another syntax in the form of the Stardog mapping syntax. And this is inspired off of the Sparkle construct. And in doing so, it lets us better describe the shape of the graph that we are going to map to. And it reuses many of the familiar parts of the Sparkle query, specifically a Sparkle construct query. So in here, we start with a mapping and the name. We have a from stanza. In this case, because it is from SQL, we have a SQL query. We can then see a series of graph patterns in the form of a to. And then we use the where clause with the bind and template function to serve as our subject URI bindings. Let's look at this at each piece. So first, the name of the mapping is optional, but typically we'll like to provide that. We have our input table, and this here, although it is from SQL in this example, Stardog does support other types. From SQL is one. There is also a from JSON, as well as a from CSV. The content of this binding will be specific to that input type. We then have our output graph, and this follows the same set of rules that you have within your basic graph patterns within a Sparkle query. And again, we can read this as a sentence with variables in certain positions. So we have the variable album is a album, so here's our fixed relationship. We then have the semicolon and as an and structure. So album is a album and has a name with the variable name, and artist with the variable artist, and a release date. Finally, the values, such as the album subject URI and the artist subject URI, are both done in a value mapping using a where clause, using bind just as you would bind a variable within a Sparkle query, and the template function as something specific here to take the values, in this case ID and artist, from the source columns and use those to create the values. Now looking at a different structure, for example, if it was a NoSQL source, we could have from JSON. And in this case, we're not using a query language, but in the from JSON stanza, we're going to express the JSON structure that we're mapping to, and then our IDs will come from positions within that structure. Now, although this comes from a different type of example data, we can follow here that we have things like ID, accounts, names, and so on. We are still going to create a to stanza showing the shape of the graph that we're going to make, and we're still going to take advantage of the value bindings to bind the subject URIs to use within our target graph. Now, we don't have to create these virtual graph mappings by hand. We can take advantage of a feature within Stardog Studio called Generate Graph. And when we create that virtual graph, one of the options is a checkbox for generating a virtual graph mapping. And essentially what Stardog is going to do is it's going to take that data source information, follow the metadata portion of a connection API to inspect the far ends schema. Based on that schema, it will then generate what we like to describe as a generally square mapping that will take tables and columns and turn them into nodes and edges. and follow primary and foreign key relationships across different node types. However, what it will not do is renormalize denormalized data. So these generated mappings are a good starting point for creating very quickly a virtual graph mapping that you can query from. But then if there are additional ways that you would like to extract that information, normalize it into a more richer graph, then you can edit this and save it within Stardog. So we like to view it as a nice code generator to get going. This concludes the section on mappings. This section is about using virtual graphs. Now, a virtual graph in Stardog has the three components we've described: the unique name, the configuration options, and the mappings for the data. Now, when we add that virtual graph outside of Studio, we can use the Stardog admin virtual command, where we have both the properties for the connection information and the mapping provided. And so common within DevOps environments and other source control environments, things like properties might be sourced from a configuration management system, mappings might be in your source control system, and when a new system is created, orchestrating this command to create your virtual graphs on the fly would be a typical common use case. And the properties files will look like any common JDBC properties file. They contain things like a JDBC URL, username and password. These properties files can contain those additional parameters for those different JDBC drivers. Common JDBC parameters are prefixed with the JDBC prefix here, and additional properties specific to that driver are prefixed with the ext for extension. Now, to manage a virtual graph, we have all the capabilities that for system administrators comfortable with the command line that are perhaps not using Studio. We can do things like remove or list a virtual graph. And then once the virtual graph has been loaded and we have mappings and properties files having been loaded into the server, we can also extract those out again. And so if you have made a whole bunch of edits and saved those, and then you want to get your mapping back out and commit it to a source control system, you can use things like the export mapping command line to do so. And when we query a virtual graph, the first way to think about it is the virtual graph is a named graph. And the only difference is that we have taken the virtual IRI prefix and the name of the virtual graph, and then otherwise we query it as any other named graph, which means we can have more than one of them in a single query. We can join that named graph, or in this case virtual graph, with other data in Stardog, and we can apply other querying features to that. So taking a look at this, we can take our virtual graph query where we have the graph stanza, in this case join it against data that might be in Stardog. And this is going to be a very popular use case where we have some amount of data that's been virtualized and other data that's been loaded in, things like reference data, things that might have been materialized, or just disparate data sets that you're going to unify in part through virtualization and in part by having it loaded into Stardog. Now, specifying that graph keyword requires us to continuously think about where particular parts of our graph are in relation to the virtual sources that serve them. And so to address that, we've added a feature called virtual transparency. And that avoids having to specify that graph stanza and virtual URI in our particular queries. Now we turn this on with a virtual transparency database property that you have to set to true. And we are given a couple of utilities to mix this in and take advantage of it. The first are some URIs. The tag Stardog API context virtual refers to all virtual graphs. The tag Stardog API context all is the union of all virtual graphs with a local graph. And this essentially enables us to simplify our queries without having to specify individual virtual graph URIs. However, in the event that we turn on the virtual transparency, and for a particular query we don't want to have it on, Stardog does have query hints that let us turn off that feature on a query-by-query basis. Now, the virtual transparency gave us a pretty broad definition of being able to simplify queries. There's another relevant feature here called named graph alias, new to Stardog 750 and later, that enables the creation of a graph URI that represents a set of named graphs and or virtual graphs that we can take advantage of. This is another database feature that we have to turn on with a graph that aliases property. And we can use this in the Sparkle protocol from named, using, and using named, so that we can avoid having to specify that graph term and the virtual graph URI as part of our queries. And so for particular lenses of information and data that want to be shared, a graph alias is a nice way to group one or more virtual graphs and named graphs together and then query them uniformly without having to keep track of individually which parts of which graphs came from which data source. Now, adding the virtual graphs to the named graph alias does require us to create a special named graph called tag Stardog API graph aliases. And from here, each alias would then have a predicate then listing out the other named graphs that are associated with it. Now, there are some limitations to this feature. We cannot use a named graph alias in a graph keyword, a construct, insert, or update, and we cannot create an alias that is a composite of other aliases. Some of these restrictions may be removed in a future release of Stardog. That is to be determined. The next feature to look at is materializing virtual graphs. We mentioned at the start of this talk that we could use the virtual graph definition in a couple ways. We can use it to dynamically query data at its source, or we can use the virtual graph feature to perform an ETL operation. This is performed using the virtual import command within Stardog. And of note, this is a command that is available today in Stardog 7.5 on the command line only. It does, however, work with other parts of Sparkle for moving graphs around, things like add and copy. We can use the virtual graph URI to a named graph URI that will then take advantage of the virtual graph definition and materialize that virtual graph en masse into that target graph. The virtual graph feature, as we mentioned, also allows importing of CSV files. And this is going to look like the other mappings. However, unlike having a SQL query, we need to only specify from CSV and then use the column headers as our variable names. Now, only imports are supported because, again, there is no query to marshal to, there is no server to talk to, and so we're going to use this with the virtual import command. And this will be a quick way to a CSV to RDF ETL using a declarative virtual mapping syntax. This concludes the section on using virtual graphs. This section is about virtual graph cache. The virtual graph cache is a relatively new feature to Stardog, and this lets us use a cache dataset in conjunction with the Stardog server to serve a variety of purposes. And these cache datasets can be an entire graph, a virtual graph, or a query result, and that last one is experimental. But typically, we would use these to cache a virtual graph or a portion of a virtual graph, especially if it doesn't update frequently, and allows us to federate queries to the remaining fully virtualized portion of that graph. So these virtual graph datasets can be cached and combined with other virtual graphs, including portions of that same virtual graph. Additionally, Stardog, as part of this feature, does support a fully managed out-of-band cache, meaning third-party tools and integrations can be used to populate that cache. So a good example of this is a portion of your data is relatively slow moving, another portion is relatively fast moving, but we want to materialize into the cache those slow moving keys and then join it with the virtual graph portion over time. And so the virtual graph cache gives us something between the two extremes of fully virtual or fully materialized. And it enables us to build cache architectures using this out-of-band feature capability. I do encourage you to take a look at the Stardog Architectures training that goes into some of those options on how you can use this in your solutions. Now, currently, all the cached feature is handled via the Stardog command line, where we can create the cache, we can clear the cache, we can copy it around, we can update the cache based on an update query and a refresh script. This concludes the section on virtual graph cache. Now that concludes the Stardog Academy training on virtual graphs. We've covered what a virtual graph is and how to configure them. We looked at how to understand virtual graph mappings and data sources and the different options available. And we looked at virtual graphs along with key other features. Thanks for following along. If you have any questions, please review our frequently asked questions page or head to stardog.com/docs for additional information.